We will now discuss combination of simple harmonic motions. Combination of simple harmonic motions. Let us consider two simple harmonic motions described by x1 equal to a1 cos omega t, and the other one is given by x2 cos of omega t plus delta, which is an epoch. Clearly, these two simple harmonic oscillations have same frequency, and the frequency is omega. They, however, have different amplitudes and phases are also different. Resultant displacement is obtained using principle of linear superposition and let the resultant be x. So x is x1 plus x2 . Let us open up so what we get is cos omega t cos of delta minus sin omega t sin of delta. So in the next step, let us take cos omega t and sin omega t common. So we have a1 plus a2 cos delta minus a2 sin delta and we have sin omega t. Let us define this to be r cos theta and this to be r sin theta. So we end up with taking r common, what we have is x equal to r cosine omega t plus theta, where r square is r cos theta whole square plus r sin theta whole square. Putting the values of r cos theta and that of r sin theta, and here we have a2 square sin square delta, which can be combined with this term. So cos square delta plus sin square delta is unity, and therefore we have a1 square plus a2 square plus twice a1 a2 cos of delta. So r is actually under root of this factor. And tan of theta can be written as r sin theta divided by r cos theta. Put the value of r sin theta and that of r cos theta. So this is the value of theta. So theta is actually tan inverse of this ratio. In this problem, we have combined two simple harmonic motions of same frequency and collinear because both are along x, and the resultant is also a simple harmonic motion. And the amplitude is given by this expression, theta is given by this expression. We now show the representation of SHMs in phasor diagram. So phase representation of SHMs. The component SHMs were x1 and x2. The amplitudes were A1 and A2, and the phases were omega t and omega t plus delta, and omega t is actually omega t plus 0. Let the omega t plus 0 line be represented by this line, and this is A1. So this is A1. Now A2 makes an angle delta with A1. So this is A2, and this angle is delta. And let us complete the corresponding parallelogram. And this is R, the resultant. Now from parallelogram law, of vector addition, which gives us R squared to be A1 square plus A2 square plus twice vector A1 dot vector A2, and the angle between A1 and A2 is delta. So in the next step we can write A1 square plus A2 square plus twice A1 A2 cosine of delta. So R is So we have reproduced the previous result. Now from triangle, so this is O, this is A, this is B, and let us extend it and let us drop a perpendicular from B onto this line, and let this be C. So from triangle OCB, so from this triangle, this angle being 90 degrees, we have tan of this angle, which let us call theta. This is BC by OC. Now this being A2, this is also A2. This is delta. So this is also delta because they are parallel. So BC is A2 sine delta. And OC is A1 plus AC. Now AC is actually A2 cos delta. So we have reproduced the earlier results. Let us now make a re-mention of the phase diagram. So first we have to identify the omega t plus 0 line. So this is actually the omega t line. Now look at the component SHMs. In this problem, the first SHM is along the omega t line or omega t plus 0 line. So A1 will be along this line. So this is actually A1, say of this length. And A2 makes an angle delta with the A1 line. So we have to draw this line making an angle delta with the omega t line. So this is A2 that makes an angle delta. Then the resultant is R as shown. So you can give arrows also. This is A1, this is A2, then this is R. And this is theta. So x1 x2 when superposed gives us x, which is r cos of omega t plus theta. All are SHMs, all are collinear, and all have same frequency omega. And this is the Phasor representation of the three simple harmonic motions. We come to the next problem. Combine x1 and x2 which are simple harmonic motions, have same frequency, and they are collinear. The resultant displacement is using principle of linear superposition. X equal to x1 plus x2, and we can put the values. Next, the cosines are opened up. So we have and now we can take common cos omega t and sin omega t. So we have A1 cos delta 1 plus A2 cos delta 2 multiplied by cos omega t minus A1 sin delta 1 plus A2 sin delta 2 multiplied by sin omega t. Let us put for this factor A cosine delta, and for this one let us put A sine of delta. We thus have And this gives us, if we take a common, and this is a simple harmonic motion of same frequency, and it is collinear. Here let us find the amplitude. So a square is this gives us the bracketed expressions square. This gives us a1 square, because cos squared delta 1 plus sin squared delta 1 is 1, plus a2 square, because cos squared delta 2 plus sin squared delta 2 is 1. Now we take 2a1 a2 from both the bracketed expressions common, and then we have cos delta 1 cos delta 2 plus sin delta 1 into sin delta 2 as the cross terms. And this is, and therefore A is under root of this quantity, and tan of delta is the ratio of A sin delta to A cos delta, which gives A1 sin delta 1 plus A2 sin delta 2 whole divided by A1 cos delta 1 plus A2 cos delta 2. Here A is the amplitude and delta represents the phase part of the resultant SHM. Let us make a phasor representation. So in the phase representation, let us collect the facts first. The component simple harmonic motions are x1 and x2, having amplitudes A1 and A2 respectively, and the phases are omega t plus delta 1, so it makes an angle delta 1 with the omega t plus 0 line, and this is omega t plus delta 2, which therefore makes an angle delta 2 with omega t plus 0 line. So this is, say, the omega t plus 0 line or the omega t line. Now let us draw the first SHM, which makes angle delta 1. So this is delta 1 and this is A1. Now at this tip we have to place A2 that makes an angle delta 2 with this omega t plus 0 line. So this is, say, delta 2 and this is A2. The resultant will be this line. So this is the resultant and it makes an angle delta with omega t line. So this is A1, this is A2, and this is A. Let us check whether the expressions of A and delta follow from this diagram. Use triangle law. So this is O, this is a B point, and let us say this is a D point. So we use triangle law to the triangle ODB to get A is equal to A1 plus A2. This gives us so A is the angle between A1 and A2 will be, this is A1 and we can extend it. This is therefore delta 1. So this is the angle between A1 and A2. This is A1, this is A2, and this is therefore delta 2 minus delta 1. So here we have cos of delta 2 minus delta 1, and A is under root of the entire expression. Next, what is tan of delta? Let us drop perpendiculars from B point. The foot say is A, and let us drop perpendicular from D. The foot is say C, and this point is say E. So tan delta is BA by OA. And BA is made up of two parts. One is AE, which is this one, and BE, divided by two parts again, OC plus CA. Now what is AE? AE is actually DC. So this is DC, which is A1 sine delta 1 plus BE is A2 sine delta 2. OC is A1 cos delta 1, and CA is actually DE, which is therefore A2 cos delta 2. Clearly, the expressions have been reproduced from this Phasor representation. So let us make a gist. The problem was x1 was given to be and x2 was another component SHM, and the two were added, and what we got was and here A was A1 cos delta 1 plus A2 cos delta 2 whole square plus A1 sin delta 1 plus A2 sin delta 2 whole square. Whole under root, and tan of delta was the ratio of these two expressions. It is clear from this gist that if we are given a large number of SHMs which are collinear, which have same frequency, we can add them in a similar way, which we show now. Combine 4 SHMs, and the SHMs given are they all have same frequency, they are collinear. So the resultant displacement of a particle on which these SHMs are applied will be by principle of linear superposition so it will be A cos of where now this is SHM, same frequency and collinear, where the amplitude will be, we can obtain from here. We have to write 4 such expressions in the form of a sum, so let us use the summation sign and write it. So let us first write it as A1 cos delta 1 plus A2 cos delta 2 plus A3 cos delta 3 plus A4 cos delta 4 whole square plus A1 sin delta 1, A2 sin delta 2, A3 sin delta 3, and the last one A4 sin delta 4 whole square. So it's better to write it in this way. Summation A cos delta whole square plus summation over A sin delta whole square under root. And so as not to confuse with this A and that A, because this is the resultant and this is the component, so let us write it as AI delta I summation over I. So this is the resultant amplitude, and similarly we can write the phase part delta as follows. So this is tan of delta, and now let us represent the SHMs in phasor diagram. So this is omega t line or omega t plus 0 line, Let us draw A1. So this is A1 at an angle delta 1 with omega t plus 0 line. Now let us draw A2, which makes angle delta 2 with omega t line. Say this is A3, which makes angle delta 3 with omega t line. And finally A4, which makes angle delta 4 with omega t plus 0 line. And the resultant will be so this is the resultant A, and this is the angle which A makes with omega t line. So the combined form of SHM is this is A and this is delta of the resultant SHM.